Hi, in this video we are going to handle the IRPMJ read in the kernel mode driver that we have been developing, and we will also send the read file API to our kernel mode driver to get the driver communicate with our application. So we will be calling the read file API in our user mode application, and driver, if it has some message for the user mode application, it will be reverting back to the user mode application. Recapping the previous videos, we have been able to develop the basic understanding of the user mode communication with our kernel mode driver. We have been developing the user mode application which communicates with our kernel mode driver. In our driver, we have been handling the write functionality whenever user mode application wants to send some message using write file API. The IRPMJ write message we have been handling in three different ways, which was direct IO, buffered IO, and the neither buffered nor direct IO. And then we also developed a user mode application to communicate with our driver, where we used the write file API to send a particular message, which was hello from user mode, to communicate with our driver. And at the driver level, we were handling that IRPMJ write request in different handlers, and we were printing that user mode message in our driver. In this video, we will be using the IRP MG read and in the driver level, and at the user mode level, we will be using the read file API to communicate with the driver. So in the read file API, at the user mode level, we will be calling the read file API, and at the kernel mode level, if the driver receives the IRPMJ read due to the read file API request from the user mode, the driver will be sending a message to the user mode that this particular message is from the driver. And in the same lines, we will be using the direct IO, buffered IO, and neither buffered nor direct IO as the main functionality. Here I see something. Let me first, a typo is there. Let me first clear the typo. We will go to here and then here and here. We have the neither buffer nor direct IO is written as neither buffer nor direct IO. Let the IRPMJ read as the direct IO. Let me the buffer nor direct IO. Okay, let me save it and publish it. Copy. Close it. Close it. And so before actually we jump into the study of read file API and how we are going to handle the read request from the user mode application in our driver, we need to first clean up some few things that we have actually missed to properly implement the our driver, so that it gracefully handles some error scenarios and some uh, some the printing of the data communication with the user mode, so it gracefully tells the user mode that this amount of information was written, this amount of information was read by the driver. So that thing we need to do first before we directly jump into the writing of handlers for IRPMJ read and that user mode application calling of read file API. So first we will go to the functions.c where we are at currently. Then we will go to the handler that we have registered, which is dispatch write buffer and dispatch write direct. So instead of directly returning the default status as success, we should have the default status as status unsuccessful, so that if anything actually fails, the status unsuccessful will be written instead of the status success. And when everything goes all right, we will be here returning the status success and the status and the status equals to status success. Apart from this, in actually the dispatch the write direct IO, we also need to check if the address, the user mode, the kernel virtual address that we got is actually valid or invalid. The so here we are actually accessing the MDL address, right? To convert that address into the kernel virtual address, we have to check if this user mode address is valid or invalid. So we have to have a null check in here. So the way we do it, if we have a logical AND np IRP of MDL address, if it is valid, if it is not null actually, then we will go ahead and get the and convert the virtual address of user mode to the virtual address of kernel mode. In the similar lines, we will be uh, handling the buffer IO for IRPMJ write. So in here, instead of status success, we will have status unsuccessful. And here we will have, if the string terminate function is successful, we will be able to correctly print out the data from the user mode. Then we will have NT status push to status success to indicate that our purpose was fulfilled in here. And in the similar lines for write neither dispatch function, we will have status unsuccessful, and then we will have the status unsuccess to tell the IIO manager that the driver has successfully processed the IRP status success. The next thing we will be doing is uh, telling the IO manager how much data was written and how much data was not written, but telling the IO manager how much data we actually uh, read from the buffer, and then we actually printed the data at the kernel level, at the driver level. So in here, in the IRPMG write handlers, what we are doing is we are processing the user mode request coming, and we are printing that user mode request. So we have to tell how much information was actually uh, written at the kernel level to the IO manager. It is not essential when handling the IRPMJ read, but it is very essential in handling the IRPMJ read. Not in IRPMJ write, but it is essential in IRPMJ read, because at the write level, the user mode need not to know how much data actually was sent to the driver. only driver can just optionally tell the IO manager or the user mode that how much data it received. It is an optional condition, but when we say we will be using read file API at the user mode level, and at the kernel level we will be sending the data from the driver to the user mode. So then we will have to tell how much data the user mode has to read from the driver. So that's why the amount of bytes the user mode has to read incoming from the driver has to be essential. So here we will be writing the function for that specific scenario where we have to tell the user mode application how much data was given to the user mode application by the driver, so that that amount of data will be returned to the user mode buffer by the driver, and that amount of data will be read by the user mode buffer by the user mode application. So first we have to actually tell now in here optionally we'll be telling the IO manager how much data we have received and we have written the at the driver level. So here we first declare a u int dword data written. Initially it will be 0. No amount of data was written to the driver when handling the IRPMG write request. So next, to get the amount of data that the user mode that the kernel level driver has received, we will be passing the extra parameter, that is the third parameter, to the is string terminated function, which will be our address to the data written. So here we have the third parameter, which will get the amount of data that the user mode application has sent, and that amount of data was written, that amount of data was received by the driver. So if this amount of data was received by the driver, then we will be telling that to the user mode application or IO manager that this amount of data was uh, received by the driver. So in this third parameter that we have to actually implement this third parameter in this is the string terminated function to fill this out parameter with this length, that this is the length of the user mode buffer. So these will be same. These has to be the same. So we will be dynamically filling this DW data written using this API that we have written in the previous video. We will be modifying this API coming up, but just first we will be modifying the functions. U int the DW data written will be 0, and then we will be passing the address of the data written, DW data written. Now in here too the same thing, this amount of data that the driver received, and at the neither call also we'll be doing the same thing. U int DW data written equals to 0. 0 bytes of data was written initially, and then we'll be filling the amount of data that was written by passing the address and telling the IO manager and user mode application that this amount of data was actually written. Next, we'll be now uh, modifying the function. This is a string terminated. So we'll be going to the definition. So in here we will be expecting a u int pointer to dw string length rngth. So we'll be receiving a pointer which will be the address, which will point to the address of the amount of data that the driver has received. We have to fill this parameter in this function. So here we will be first clearing out that initially nothing was written. pww tearing length equals to 0. Next we will be filling the amount of data that is written. So here we'll be dereferencing the dword pointer to dword string length equals to. So now if so this while loop, what it is doing, it is traversing the string till the length that we have received is less than the index. The index is less than the length. So we are going through all the length of the string until we encounter the uh, null character. When and if we have not encountered the null character, we will be increasing the index of the string. So one by one, we will be traversing every character of the string. So this will be storing the number of characters present in the string that we have received in this function. But we have to also tell the in here we have to tell the amount of characters that we have parsed in the string. So it will be same as ui index, but in here we will be also telling that it has parsed null also. This way the null character is also read by the driver, and apart from that the whole string is read for the driver that the string was coming from the user mode. The driver has read that string, also the null character present in that string. So it gracefully tells the user mode application this out parameter fills this API fills the out parameter in this way, and the out parameter is returned to whoever was the caller, whether it be write neither, write buffer, or write direct. So when the out parameter was returned, this will be filled after calling this function is string terminated, and we then communicate with the IO manager that this amount of information was received by the driver from the user mode application. Next we will be going to the 6strings.h and modifying the declaration. So the same thing will be happening. U int pointer to pw length ength. So the same thing has happened. Okay. Now apart from this, nothing is there for us to modify. We will handle every error scenario, or we should say gracefully telling the IO manager that amount of data is written, and gracefully telling the IO manager if the IRPMJ write handler was success or unsuccessful. So next we will be diving in the read functionality, how we will be handling the read file API using IRPMJ read from the user mode perspective and kernel level driver perspective. First, we will be reading about read file API. Unlike writing operations, write file, where tracking the number of bytes written might be optional, read file API must correctly report the amount of data read. So it says that the amount of data written, telling the IO manager or the user mode application here using write file API is an optional thing. But when using read file API, the amount of data the user mode application has to read has to be told to the IO manager and user mode application. This ensures user mode application receives the right amount of data. It also helps the IO manager handle user mode memory buffer updates properly. So it ensures the user mode applications receive the right amount of data, but it also helps our driver and the IO manager at the user mode buffer that the driver and IO manager has received updates properly. The IO manager uses temporary kernel buffer to hold data that must be copied to the user mode memory buffer. The amount of data to be copied must be specified to avoid incomplete or empty results. So the IO manager uses a temporary buffer to hold the amount of data that must be copied to the user mode memory buffer. So the IO manager has a temporary kernel buffer that holds the data that must be copied to the user mode memory buffer. The amount of data to be copied must be specified to avoid incomplete or empty results. So by the driver, the amount of data that is copied to that temporary kernel buffer at the driver level must be specified by the driver itself. That this amount of data was copied to that temporary kernel buffer so that the IO manager is informed that this amount of data now the temporary kernel buffer has and uh, user mode application will be accessing this amount of this amount of buffer data that the driver has filled. So to start the implementation now, we will be we'll be having the same thing like we have the we have the handlers registered for IRPMJ read request, which is direct IO, buffered IO, and direct nor buffered IO, nor direct nor neither direct nor buffered IO. The similar lines, we will be registering the event handlers for IRPMJ read, which will be the same direct IO, buffered IO, and neither buffered nor direct IO. So the first thing that we will be doing is removing the this dispatch read function, because we will be now specifically defining like these dispatch write dispatch write direct dispatch write buffered dispatch write neither. In the similar lines, we'll be declaring dispatch read direct buffered neither. So now we have removed this. We'll be now to going back to functions.c. Also we will be removing uh, removing the definition of the function, as we have removed the declaration. Here is the definition, we'll be removing it. Next we will be going back to the sixthings.h, and we will be de- declaring the dispatch read direct buffer and neither in the similar lines. We will be copying these declarations and pasting in here. We will be saying read read. We have said that. Next we have to now go to the definition to use these functions. So if the use direct is defined, then we will be using redirect IO way of handling the IRPMG read and IRPMG write request. So in the similar lines, we will be defining the use write function, use read function, use read function. Similarly, the buffer, when the driver choose to handle the IO coming from the user mode in use buffer way, we will be defining the use read function as dispatch read buffer dive. If nothing is defined, then we will be defining use read function as read neither. Read neither. Now we will go into sixwings.c, and instead of registering the function as dispatch read, we will register it as use read function. Whatever we have defined use read as, if not defined also, we will be going with it. So here in above we will be defining if the driver handles the IO request as use direct or use buffered. If nothing is defined, the read and write IRPM's read and write IO operations will be handled as dispatch write neither and dispatch read neither. So next we will be now going to the functions.c, and in the similar lines as dispatch write direct IO, dispatch write buffered IO, dispatch write neither buffer nor direct IO, we will be defining dispatch read direct IO, dispatch read buffered IO, dispatch read neither buffer nor direct IO. So instead of writing everything again, we will be just copying all of this and pasting below this. Because the functionality, the core functionality will actually remains the same. We will just have to modify a few things here and there. This will be read also. Now, the first thing that we have to do is tell modify this unsuccessful message. Why we have to modify the unsuccessful messages, as we have to read the user mode buffer to write to it at the driver level. We have to verify whether the user mode buffer is actually big enough for the kernel level driver, this kernel level driver to write to. So here we will be modifying the message as status buffer too small. So if the user mode buffer that the driver is receiving, whether be it in the form of direct IO or buffered IO or write neither nor direct IO or direct nor this buffered IO, the default value of anti status that we will be uh, giving to the IO manager or user mode application will be status buffer too small. If the buffer is too small, then the driver will not be writing to that buffer. So the same message will be there here and here. Before jumping and writing more code, we will just we will be just seeing the notes for direct IO for read functionality. The function dispatch write IO handles a read request IRPMJ read using direct IO. It retrieves data from kernel and writes it into the user mode buffer via IRP's memory descriptor list MDL. So it reads the it actually writes into the user mode buffer via IRP's memory descriptor list, which is just the same that we have already read, which is converting the user mode virtual address into kernel mode virtual address. So this was the user mode virtual address, and using this function mmget system address for MDL safe converts that user mode virtual address into kernel mode virtual address for us to write data into the buffer that the user mode has sent. The MDL describes the memory in user mode. So it is describing this MDL address is describing the user mode address. The function maps it to kernel mode address using get and get system address for MDL safe. So here we are also in the code snippet we are validating and copying the data. Check if user mode buffer is valid. P read data buffer. So when we've got the user mode buffer, we have to check if the user mode buffer is valid or invalid. So we check that. If it can hold the data, p IO stack pointer to IO stack IRP parameters read.length is greater than DW data size. So we also then check if the user mode buffer can actually hold the data that we are about to copy to that user mode buffer. Check if the DW data size, which is a parameter that we have filled in here, the size of data that we are going to copy to the user mode buffer. If the user mode buffer read length is actually greater than or equal to, not write length but read length, because user mode buffer has to read the data, not write the data from the kernel driver that the kernel driver will be sending. So if this is the case, then we are actually copying the data we have to send to the user mode to that uh, buffer that we have received in the direct type, that buffer pointer that we have been pointing, the kernel mode virtual address uh, space that we have converted using this function. So we point to the user mode buffer in simple terms using the kernel mode virtual address, and we write data to it, and then we also tell how much data to read. So this is the amount of data that we are telling the user mode application to read, but we can also see that this is the amount of data that the driver has written to the user mode buffer. So here we have declared this read for simplicity, that the driver is telling the user mode buffer to read this amount of data, and informing the IO manager as well. Use RTL copy memory, a kernel safe wrapper around memcopy to copy data from kernel buffer, p return data to map to the mapped user buffer. So we use this API RTL copy memory to copy the kernel mode memory buffer to copy the kernel mode data to the user mode uh, buffer. P return data. The p return data will be holding what? P return data is this one. So this is the data that we have been writing. So next we have also error handling. The function ensures appropriate error codes status buffer too small if the buffer provided by user mode is insufficient. So if anything that goes wrong, like the length of the user mode buffer is small, then we will be not writing the data to the user mode buffer, and we will be telling the IO manager as well as the user mode buffer that the buffer that user mode has sent is too small. So now we will be modifying this function further. So first thing we have to modify is get is define the data we will be sending to the user mode. So we will define a pchar for it. Pchar p return data will be dispatch read direct IO hello from the kernel. This is the data that the driver is going to write, and its length will be u in dw data size equals to size of this. This is the length of the buffer that user mode will be receiving from the driver. Next, we have to define, we have to declare first the read data buffer. So read, uh, we have to declare that write data buffer is there, right? So we have to declare the read data buffer. Read. So we have declared a read buffer in here, and this will be the amount of data that user mode first read. User mode will be reading. So after this, we'll be modifying this read. This will be storing the buffer of user mode with kernel virtual address. If we get the user mode buffer with converted kernel mode virtual address, we will be checking if the we will be next what we will be doing is, here we will not need actually this thing as a string terminate because nothing has been written to anywhere. So here when we have got the kernel mode virtual address, we have to get the we have to what we have to do, we have to get we have to check the buffer is small or big for us to write, for the driver to write to it. So in this if condition we will be checking if the buffer is small or big, that user mode buffer that we have received. In p I use stack irp, which will be pointing to the IO in the IRP stack for this particular request. Parameters dot read dot length is greater than equals to dw data size. dw data size stores the size of data that we want to write, and if the read length is greater for the user mode, if this is the read length for the user mode that the user mode will be reading. If it is the case, then we will call rtl copy memory to copy the amount of data to that kernel virtual address which is pointing to the user mode buffer. The first parameter will be destination will be the kernel virtual address of the user mode buffer. Next will be the length rtl copy memory. Okay, So next will be the source, actually, not the length. I don't know why it is saying the length. It's a source only. Yes, yes, it is saying the source and then length. So then the next will be the source. The source will be the this one, p return data. This is the data that we will be copying to the user mode buffer, which is being pointed by kernel mode virtual address. And the next will be the length, the amount of data that the user mode has to read. So this will be dw data size. Now we have everything. So this is the in this from this API we have copied the uh, buffer from the driver to the user mode buffer. So now we will say how much amount of data the user mode has to read, which will be dw data size. This is the amount of data that user mode has to read, and we will at the end have the NT status as a status success. At the end we will be returning the status success. So here the amount of data will be specified, the amount of data that the user mode has to read, or the amount of data that the driver has written to the user mode buffer. So now another thing that we have, I think everything is covered. MDL is safe. So this is also we have already error handled. If we get the correct user mode address of the user mode buffer, we have validated that as well. So nothing is there, I think. One thing is there. So we are print statement is wrong. Dispatch read direct IO. Dispatch read direct IO. Buffer too small. Small. Nothing is there, I think. Okay. So next in the same lines we will be modifying the read buffered and read neither. So read buffer will also be very simple. We will be copying this and pasting it in here, and this will be the read buffer, read data buffer, and this will be the read data. So this all declaration is done in the buffered IO. Read buffered IO we will be now handling, and this will be containing the user mode buffer. The now we have the user mode buffer. Here we will not be doing this. We will be doing this if it is a valid thing, and the same condition will be there which we have in here. If the read length is greater than the amount of data that we are writing in the user mode buffer, then we will be writing the data. This one and this one, read buffer, we get the system buffer, and then we write the data to it. The system buffer job, what was happening in the buffered IO, that the IO manager was allocating a non-paged memory, and at that non-paged memory we are writing. so that user mode will be accessing this, and the IO manager will be coming into the picture for this specific scenario. So for a smaller buffer, the buffered IO was used for communication. So the amount of data that the user mode has to read is this one, and everything I think is same. For the buffered IO, it is fine. Now we have read neither. The same thing we will be doing. We will have this. We copied in here. Read and read, and this dispatch write neither. Instead of it is will be read neither. Let's correct the indentation. So in here, when we were handling the IRPMG write requests as write neither, we were probe to read. We were using the probe to read API, but instead of using probe to read API, we will be using probe to write API now. Why? Because now we have to write to this user mode buffer directly. If this user mode buffer is pointed to an invalid memory or is not accessible somehow, then there is a problem. We don't want the read functionality, because in write call, user mode was sending some data to the driver and we were reading that data and printing that data. But in here, when IRPMG read request is come from the user mode read file API, then we have to write. The driver's job is to write the data to that buffer that the IO manager has sent user buffer directly. So we have to write. So therefore we have to use probe for write. So let's study some more things about this. Buffered IO will remain the same. Neither buffer nor direct IO. Probe for read. Probe for write. So this is this snippet that we are modifying. Probe for write is used in dispatch read code. Probe for read, probe for write is used in dispatch read neither code, because the driver purpose in a read operation is to write data into user mode buffer. So why we have used probe for write? Because the driver's job in this case is to write the data into the user mode buffer, not to read the data from the user mode buffer. The function ensures the buffer is writable and prevents crashes or vulnerabilities caused by invalid memory access. Using probe for read in this scenario would be incorrect, as it only validates read access, not write access. So if we had used the previously used probe for read, it would have only validated the read access, not the write access, and it was vulnerable to the crashes and the error invalid memory access vulnerabilities. So that's why we have used the probe for write function. So we'll be using the probe for write function, and in the same way we will be accessing the read data buffer. Okay, probe for write, we access the user mode buffer in here, and then we don't need this. We will be copying the data. As we are directly accessing the buffer also, you do not need a if condition in here too. We will be just copying the data to get buffer. Read buffer, we copy the data, and the exception handler is there, and at the end of the day we return the amount of bytes that user mode has to read. This completes the uh, kernel driver code. Next, we will be writing the user mode application, which will be using the read file API in the upcoming video.